The next topic is the digital modulation techniques, right? Uh, So in digital modulation technique, very similar to the analog modulation technique, we try to change the amplitude or frequency or phase of a very high frequency carrier signal according to the changes in the amplitude of a lower frequency message signal. So the point is very clear here. Whatever message signal you send should have lower frequency. Whatever the carrier you are going to use will have a higher frequency, right? But because of this being a digital modulation, the message signal is a digital form. Digital in the sense levels, like binary means two levels, or any other M array means any other levels. Okay, so that's what is assumed here. So input will be a square wave. That's what is expected. Square wave containing the various levels. So only that is a change compared to our proper analog modulation. Okay, so input message is digital. Normally that is represented in the binary form. So what are the various options we have? Very similar to the analog, we have amplitude modulation equivalent. The equivalent is called as the amplitude shift key, right? Then equivalent of frequency modulation is frequency shift key. Equivalent of the phase modulation is phase shift key. So in each of the case, first case amplitude will of the carrier changes. Second case frequency. So frequency of the carrier will be altered. And the third case is the phase. So phase of the carrier gets changed according to the message. All right. Now, what are the other requirements? Whatever, whenever I say, okay, I'm going for a digital modulation technique like this, what are your expectations? So normally, I want to send my message to a longer distance, right? So whenever you need that, you are going to do that, you have to have modulation because, right, modulation high frequency will carry the signal for a larger distance, right? So that was a normal one, but when it comes to the digital modulation, we use the features of digital as well. So digital in the sense I am trying to send message in the form of bits or symbols or something similar to that. So I want to send more symbols, right, in a given duration of time to get a to achieve certain data rate. So normally speaking, this data rate should be very high. Okay, it's a high data. Okay, then right, what is whatever the amount of power you want to supply for this communication device, it should be less. So minimum transmission power, right? I want to include right the I want to send the data using very less amount of frequency, so minimum bandwidth. Right. So they should not be, right. We cannot say they should not be interference because that's the normal characteristic of a channel to cause interference. But you should have some immunity to the interference. So that's the next point. Maximum as you want to maximize this immunity. Then minimum circuit complexity and the cost. So everything you want to achieve comes at a cost, but always you want to minimize, and you don't want to have a very complicated circuit. You want to keep it as simple as possible, right? Then this is a very important when, so all the above, let's say we achieve somehow, right? But at the same time, on the receiver side there should be very less amount of error. The chance of making error should be less. That's what we call as minimum probability of error. Okay, now let us try to plot the waveforms, how the ASK, FSK, and PSK are going to look like for the given data, which is 1001011. So for the first ASK plot, I'm using only one carrier because either you, whenever one is there, you send the signal. When zero is there, you don't send the signal. That's all. So C of T is equal to AC sine of 2 pi FCT. Sine or cos, doesn't matter, anything you can use. Okay. So when one is there, you plot. Zero means no plot, right? Zero. One again you plot. Zero is no plot, and so. Okay, that's what this is. That's what is the ASK. Then we go for a PSK where phase of the signal gets changed, right? So uh, actually the phases can be any value from 0 to 360. But for simplicity, what we do, this is a convention. if you have two phases, divide the 360 by 2, right? One will be 0, other one will be the 360 by 2. That will be the 2 points or two phases which you are going to use. So according to that, I have to use, now I have two symbols, 0 and 1. So two phases you get. So what are the two phases? One is 0 and one is 180 or 5. Okay, so that's how you get this. So two phases are, so whenever you send one of the symbol, send the 0 phase. Whenever you send the other symbol, you add a phase of 180 degree to that and send. That's what is the phase shift key. So you see, whenever one is there, normally you draw a sign. But as soon as there is a change in the phase required for a symbol being changed to 0, reverse it. In the sense, you can see the red marks over here. There the phase is said to be changing, right? Signal is going up, all of a sudden signal comes down means change of phase. Okay, that's what is change of phase. So whenever 0 changes to 1, 1 changes to 0, 0 changes to 1, etc. happens. Yes, right. So 360 gets divided by the number of symbols. In the sense, same logic is applied when you have, say, 4 different signals. That's called as a QPSK, quadrature PSK, right? So 4 things will get 4 different angles. Okay, so like that. That's because you divide 360 by and so on. And yeah, that's about the PSK waveform. Then we have FSK. FSK means phase should change according to the not phase, sorry, frequency should change. Sorry, I correct. Frequency should change according to the message signal. All right. So we see that the message signal, there are two messages, so I need two frequencies, right? So we take two values, F1 and F2, right? C1 of t is AC sine 2 pi F1t, other one is AC sine 2 pi F2t. Okay, all right. So you see, whenever one is sent, right? I am assuming here in this case, F1 is greater than F2. The first signal C1 of t has a higher frequency than the C2 of t, that is F2, right? So you see, when 1 is sent, I am having more oscillation. When 0 is being sent, I am having lesser oscillations. Okay, just verify. Right, so first one bit duration very high, then low frequency, again high frequency because it's a 1, followed by low frequency because of 0, then 1 high frequency. So right, C1 of t, so if you want to read the signal name from the first, so first one is C1, then C2, and again C1, C2, C1, C1, because it's 100 101. That's it. Okay, this is how you can plot, right? Normally, again, the plotting question can also be asked usually. All right, give an example. Right, now coming to the design of our communication system, depending upon what type of receiver you have, there are two broad classes. Okay, first is called as a coherent, second one is called as a non-coherent. Generally, the coherent is the word used whenever you know something, right? So there is a synchronization between the transmitter and the receiver is called as a coherence, right? They work in coherence, indicating that what carrier has been used on the transmitter side is known by the receiver. So receiver can directly use that carrier directly. Okay, so that's why it is called as a coherent detector, right? Then you have another one that is non-coherent, where there is no idea about what carrier has been used on the transmitter side. Receiver has to have an extra circuit to do an estimation. Okay, so circuit becomes complex in that, right? So that's what is a non-coherent detector. Fine. So let's start with the uh, modulation techniques one by one. So first we'll see the ASK, amplitude shift keying. This is also called. So in PSK, the phase of the carrier is changed according to the message signal. Correct? Okay. So let's try to look at that. So we have two phases. So you can see S1 of t for symbol 1. S1 of t is denoted as root of 2 EV by 2b cos of 2 pi etc. Okay. Similarly, you have to choose a different signal for the 0, but that should be an addition of phase of 180. That's all. So I write the same function and I added pi to that. So cos of pi plus theta is a minus cos theta. That's what is uh, the fundamentals of trigonometry says, right? So cos of pi plus theta is minus cos theta. So I can simply write minus of the same function, right? Without the pi. So that will be for symbol 0. Is it okay? Right. So when I compare both S1 of t and this S2 of t, the function is same, right? Only the plus and minus sign are changing here. So first one is positive and S2 of t is negative. That means how many functions or how many basis functions I need? I need only one, right? And that single function we try to call as phi1 of t, which is root of 2 by tb into cos of 2 pi fct. Right? So again, every time we need to mention the 0 less than t less than tb because it's going to be sent during that relation. Okay, right. So now how do I get back my S1 and S2 from this phi1? Either you multiply by root EB or minus root EB, right? That is the energy content of the both plus 1 and minus 1, plus 1 in the sense 1 and 0, right? Okay. So we look at the modulator, how the modulator looks like. Modulator is going to look like this. So I either send a plus root EB or minus root EB. I simply multiply that with the required phi1, right? Phi1 is root of 2 by tb into cos 2 by fct, right? So you get the output. Okay. So whenever you have this, right, the input has the two different levels, right? The signal is going to have its PSD like this. This is what we derived in the previous chapter. Okay, for NRZ format, this is the case. But you see, now what you have, you don't have this as it is. This is getting multiplied by cos function. So that means you are converting your baseband into the band pass. So general representation of band pass in terms of the power spectral density is this SS of F, that equation. Okay, so substitute over there, every f becomes f minus fc and f plus fc, because when you multiply by cos of fc, right, every signal will be shifted to plus fc and minus fc. Is it okay? Yes. Now we plot that. So you can see that this is how the SB of it, the baseband signal has the power spectral density, which we derived in already in the previous classes, right? This is how it looks like. Okay, so SP of f, whatever we have plotted here, it has a highest magnitude of a square t, right? So that's the first thing. Now what you do, you need to shift this either to left or to right. Both ways you need to shift. So first it gets shifted to left by minus fc. Whatever is at 0 will be at minus fc. So whatever is at minus 1 by tb will go to minus fc minus 1 by tb. Okay, and minus fc plus 1 by tb and so on. So we wrote only few points here, but anyway, so we can write other values also. So you can see it's also equation. Yes, sure. This is a complete set of equations. So whenever you have a signal plus or minus root eb, its PSD is sp of f, right? That's for a nrz format. Okay. Now, whenever you convert into whenever you convert into the baseband into the band pass, right? This is the equation SS of f. So substitute the specific SB of f here to get this answer and plot it. Those are the two plots. Is it fine? Okay. Right. Now, let's look at the decision region. Where should be the decision boundary should be kept so that you can design the receiver part, right? So we see, right, this is called as a correlation, right, type of receiver, where the received signal S1 is multiplied with phi1, right, to get one of the answer. So one of the possible answer is S11, which is root E. Okay. At the same time, you have another multiplication possible. That is, assume that you received S2 and multiply with phi1 to get a minus root E. So these are the two possibilities. You see where they lie. So root EB on the right side of the vertical axis or the y-axis, at the same time minus root EB on the other side. So that means at the center, which is at 0, you can place the decision boundary. So let's assume that the x1 is the received. If x1 is present in the right side region, that is region Z1, you call it as a symbol 1. If it lies on the left hand side, you call it as a symbol 0. All right. So according to that, we designed this receiver. So you see, you receive x of t, multiply by any phi of t and integrate. So there is a integrate. So I don't want all the continuous symbols. I want the sample. So you sample and obtain the sample as x1. Okay. Depending upon the x1 and comparing with the threshold, you give a decision. So it is 1. The decision is given in this way. Which block? So altogether, integration plus this multiplication is called as a correlator. Okay, altogether. But no, it's just called as, so you see the equation is all together. Multiplication of phi 1 with x1 and integration. All together you do that. Okay, that's why it's generally called as a correlation. I perform the correlation. Okay, so we call it as this whole part together, x of t is correlated with phi 1 of t, means you get the output of the integrate. Right, that's how we try to represent it. Right? Okay, block diagram is clear. Okay, so this is the thresholding part, right? So decision taken in this way. So so V threshold is 0. So x1 is greater than 0, it is 1, otherwise it is 0. Okay, right. Now we move on to the next derivation under this case, that is the probability of error. Right. So we have to analyze what happens when 0 was sent and what happens when 1 was sent. So we start with received signal in presence of noise when 0 was sent. Only when there is noise you can say that there is error. Okay, right. So x of t will be 0, means it is s2 of t plus w. Right. So what happens? Whatever is received directly get correlated. So you see next sentence is correlator output. That is the output of the integrator block. You see whatever is received x of t multiplied with phi 1 of t dt and integration. So replace x of t as s2 plus w, where s2 is the signal, w is the noise. Okay. Right now we are doing for 0. Later on we'll do for every derivation of probability of error will have two parts. First you consider what happens when 1, then you consider what happens when it is 0. Okay, 0 or 1 you can interchange, doesn't it? Okay, so according to this, right now I split the integral, right? S2 of t phi 1 of t dt and w of t phi 1 of t dt. Right. So whenever you get right, whenever you perform the S2 into phi 1 dt, the answer is anyway, since there are no equations here, we cannot write what exactly you get an answer. We denote it as S21. Okay, some answer comes, that is S21 plus W. Okay, fine. But S21 is already written there. Earlier we assumed what is S21 and what is S1. You see, S11 is root EV, S21 is minus root EV. Right. So that we substitute. When we have S21, it is minus root EV plus 1. So whenever you have a received sample, you can directly calculate its expected value and the variance, mean and the variance. W1 is a noise, right? So W into phi, right? W is also a function. W is getting multiplied with phi, you get another answer, right? Integrate, you get an answer. So that is W. So my received signal, the indication is that equation 2 says that my received symbol x1 has a component that is coming because of the sent sample, that is S21, and it also has another component that is coming because of the noise. Right? So you see W1, I just explained here. What is this? It's a sample of capital W1, which is a Gaussian random. Everything we already know that. It has a 0 mean, it has this much variance and so on. Right? I just have to write it. That's all. Okay, you calculate the mean of this received sample x1. So E of x1 is equal to x1 is already calculated minus root EB plus W. Right? So separate it and calculate. You get minus of root EB because noise mean is 0. It's already assumed and it's a known fact. Noise has 0. So because of that, we are writing in this book. It's okay. So normally the expectation is a mu. So I wrote mu. Okay. Right. Then you see variance of x1. Once again, apply the same rule. Variance of a constant or known signal is 0. Variance of a noise is n naught by 2. So that is denoted as sigma square. Right. So when you know the mean and variance, and it is already known that this noise or this whole process is a Gaussian variable, so you can write a Gaussian PDF first. So to write a PDF, you should know mean and variance. That's why we calculated that those two first. Okay, so this is the notation that says PDF of capital X1 when the symbol 0 was sent. In the sense, you already know that 0 was sent. So you write it as a condition. So fx1 of small letter x1, given that line represents a given that 0 was sent. That's why this is the notation. So substitute 1 by root of 2 pi sigma square e to the power minus x1 minus mu whole square by 2 sigma square is the standard equation of a Gaussian random variable. It's a PDF. Okay. So I take it directly because I assumed my whole thing is a Gaussian representation. So then I substitute whatever mean and variance I found just now. So when you substitute, you get this equation number 3. Okay, right. So when 0 was sent, error happens when x1 is greater than 0. So what I am supposed to do, this is the fundamental idea. If you have a PDF with you, integrating the PDF gives you the probability. So this is what I want a probability, right? I just apply the condition required to calculate the probability. So P of 0 is, in a sense, probability of whenever 0 was sent, whatever is the probability. That's what is P of 0. It's a probability that received symbol x1 is greater than 0 whenever 0 was sent. So this is what is my notation. The region denoted as x1 greater than 0 means it can be 0 to infinity. So see, the limit changes. Only the limit is defined by this condition. Okay, so substitute that equation just now we derived here. Equation 3, what we have, we substitute here. Okay, in this equation, you substitute as x1 of x1 comma 0, substitute and you get this. All right, now the fundamental idea is that I cannot integrate directly because of that's what calculus says. You cannot integrate this directly, make a substitution, right? Put u is equal to something like this, and there is a dx1. So you need to substitute for x1 as well. Okay, dx1 is root of n naught into u. So need to change the limits as well. 0 to infinity will be changed into root EB by n naught to infinity. Right, so you get this. So the n naught cancels. Then whatever you get at the end is a error function, very standard function in mathematics. Okay, right. So that function is itself is substituted over here. That is equation number 4. So this is the whole calculation when the sent symbol was 0. Right. Very similar to that, we have to do it once again for symbol 1. So symbol 1 means I have to represent the signal x of t as it is s1 of t plus the noise component w of t. Okay, so we'll calculate that corresponding to symbol 1, right? And that symbol 1 is nothing but s1 of t plus w. So when I have x of t written as, right, this one, right? You see here, that is equation number 5. So I will try to get the output of the correlator, which is the integration 0 to tb, x of t, phi 1 of t dt. So substitute x of t as s1 plus w, split the integral, right? I split the integral and I substitute the answers. S1 into phi 1 is S11, W1 into phi 1 is W. So that is equation number 6. Now we should try to find the mean and variance like we did earlier. So mean comes to be root EB and variance comes to be n naught by 2. Okay. So as you have a mean and variance, directly calculate the PDF, right? So get the original equation of Gaussian variable and substitute the mean and the variance according to that. So mean is root EB, variance is n naught by 2. So 2 cancels and you are left with the pi n. Then now you decide what is the condition. Yeah, yeah. Sigma square is n naught by 2. You see here, right? This is the variance is sigma square. Okay, right. So sigma square is n naught by 2. So 2 cancels, you are left with the pi n. Okay. Now you have to decide what should be the limit of the integration so that I can get the probability from this PDF. Right. So x1 should be less than 0. Less than 0 means anywhere between minus infinity to 0. So limit changes according to that. And we substitute the PDF we calculate. Huh. Error. It is error. So I am looking at the error, right? So when you send one, error happens if it is received lesser than 0. Correct? Right. That's all. So same thing is for 0 also. See, 0 is sent. Error happens whenever it is received on the right side. That's all. We are writing the condition only for error because yeah, our concentration now is to find out the probability of error. Right. So we separate the problem. Our problem is split up into two cases. One when 0 was sent. Second part when 1 was sent. Okay. So that's why every derivation of probability of error has two parts. All right. Okay. So where were we? Okay. So we put the condition. So error happens when minus infinity to 0 fx1 of x1 into p. Substitute the fx1 of x1 over here. You get this equation. Again, you cannot integrate directly. Make a substitution, right? And change the limits, right? So original limits will be minus infinity to 0, but that will change from minus infinity to minus of root EB by n. So those two new limits, you put it in the integration, right? So PE of 1 is equal to, substitute the value. So say that is minus infinity to minus of root EB by n naught, exponential of minus u square into d. There was a n naught which gets cancelled with the n naught, root n naught in the denominator. And we are left out with the term, which is once again a very standard error function. That is equation number 8. Right? So in order to calculate the total error, it's an average value. So we need the probability of generation of the symbols. And since we don't have any idea about that, we assume that this is equiprobable. How many zeros are generated? So many number of ones are also generated, but at random. Okay. So look at the equation, probability of error, P is equal to probability of 0 into probability of error when 0 was sent plus probability of 1 into probability of error when 1 was sent. So substitute the values and you get the final answer. PE is equal to half error function of root EB by n. Is it okay? Right. So that is the equation for probability of error when you use the PSK as the modulation technique. All right. Okay, let's proceed further. Next, we'll move on to the FSK. Okay. Now we have, we know that from the graph we plotted earlier, FSK requires two different frequencies, which means I have to generate two different signals. Correct? So two different signals are like this. S1 of t denoted by root of 2 EB by TB cos of 2 pi of 1 t. S2 is same amplitude, but the frequency is F2. Right. So there is a condition. This is actually required that whenever you have the sampling coming into picture, that is 1 by TB, the frequency should be integer multiple of 1 by TB. So because of that, we write this. F1 is N1 by TB, F2 is N2 by TB, N1 and N2 are the integers. So since you have two different S1 and S2, two different functions, it obviously means that I need two basis functions, isn't it? So I need two basis functions. So let's try to call the basis functions as phi1 and phi2. So this is how the basis functions look like, right? Phi1 is root of 2 by TB into cos 2 pi f1t. Phi2 is root of 2 by TB cos 2 pi f2t. Right, f1 and f2 are the variables here. Uh, Depending on that, I will be able to define what is phi1, what is phi2. Okay, right. Then S1 of t can be written as root EB into phi1. S2 is root EB into phi2. So root EB will not change. That's what is the message symbol. Okay. Now, so since there are two different what you call the basis functions, whenever you send one symbol like symbol 1 or symbol 2, you will be able to multiply that with the two different signals to get two different answers, indicating that this is a two-dimensional problem, not a single dimension. So every point in space has two values to what you call you have two values to represent that, like x and y coordinates. So you try to write that as this. So how to calculate that value? Whenever the first symbol S1 has been sent, right, the representation of that in space is root EB comma 0. This is how you calculate. S11 is S1 phi1 dt, the integration, which is root EB. S12 is S1 into phi2. They are orthogonal in the sense they are in the different direction, so you don't have an answer. Okay, so yeah, second one is 0. Okay, so this means first this is the x coordinate, this is the y coordinate. Okay, so you try to write it in that way. So one along one axis, the second value along the other axis. Normally you see this is actually the convention here is you are not writing x and y because there is no xy axis. There are two axes which are phi1 and phi2 axis. Okay, you can see this diagram. I'll come to this later, but you see the axis now. One is phi1, one is phi2. Okay, so whatever you write first, that is the first value, in this case root EB, it is corresponding to the phi1. Okay, and 0 corresponds to phi2. So in order to reach this point S1, you need to move root EB along phi1 axis, and you don't have to move, right, you don't have to move a bit along the y-axis, or sorry, not y-axis, phi2 axis. That's what is the meaning. Okay. Say similarly, you can calculate for S2 of t. When you have S2 of t, S2 into phi1, they are orthogonal, so 0. S2 into phi2 is root EB because S2 and phi2 are in the same direction. Is it okay? So now you see the first value is 0. That's why you write a 0 here. You are not using the x coordinate or the phi1 coordinate, but you are using the phi2 coordinate as root EB. Now let's try to mark those points. You see, phi1 and phi2 have been chosen. They are perpendicular because you call it as the orthonormal basis functions. Orthonormal in the sense they satisfy this condition, right? Whatever condition you see, there are two functions. Phi1 into phi2 is 0 and phi1 into phi1 integration will give you 1. Phi1 and phi2, whatever we have considered so far. Okay. Right, let us try to mark them on the phi1, phi2 axis. So it's a plane on that I mark. So S1 is marked along the phi1 axis. You can see that over here. Similarly, on the phi2 axis, we mark the S2 point, which is here. Normally, the decision boundary is considered at the center. So in order to identify the center, we connect S1 and S2 and bisect that line. So that line will be x1 equal to x2. So we come to know that there is, I can design a decision boundary provided whenever it is, whenever the point is above the x1 equal to x2 line, it is s2 that correspond to x1 less than s2, sorry, x1 less than x2, right? So that's what is the region 2 I have written over here. Similarly, you can see that for any point lying on the right side of the x1 equal to x2, that should correspond to region 1, x1 greater than x2, right? Okay, so then we'll see the model generation or the modulation process. On the modulator side, this is the block diagram. I have binary sequence coming from here. I need to, if it is 1, I use this part. If it is 0, I use this part ultimately. So whenever it is 1, m of t gets multiplied with phi 1 of t and you get s1 of t. Whenever it is 0, 0 gets converted into a not, passed to a not way to get 0 into 1. So this becomes 1 so that you get multiplied with phi 2 of t, which comes as a s2 of t. Add them together to get the FSK wave. Okay. Similarly, demodulation is also pretty much similar. Again, this demodulator is assumed to be you know the frequency. It's a coherent detector. So phi 1 and phi 2 are known. So once you receive the signal, split it into two parts, right? One part gets multiplied with phi 1, other part will get multiplied with phi 2, right? So if at all you have the signal which consists of the S1, the phi 1 into this integral will give you an x1. Okay. At the same time, if this has a other part, this is going to give you x2. So what we do, we subtract x1 minus x2 will be considered as a y. Okay. Depending upon what is the value of y, right, we will make a decision by comparing that y with the z. Is it okay? So y greater than 0 means it is 1, y less than 0 means it is 0. Okay, so that's how the decision process takes place inside the demodulator. Now, our intention is to calculate the probability of error once again for this FSK. So, any symbol you received is represented in x equal to x1 comma x2, where x1 is the result of the upper part, x2 is the result of the lower part. How do you calculate that? You see here, x1 is equal to 0 to tb x of t phi 1 of t dt upper part, x2 is equal to integration x2 into phi 2 of dt over the period 0 to tb, that's the lower part, correct? Now I'll come back. So if at all you send a symbol 1, this is how the equation looks like, because it has a s1 component plus a noise. If you send a symbol 0, then this should look like s2 plus w, because s2 is the symbol for 0, isn't it? S2 is the format used for sending a 0. Is it okay? Okay. Right. Now, let's move further. Let us try to denote what is called as, we denote a variable y, right? This is because I have to compare this y with the threshold. All right. So I am not using x1, x2 as it is. I am using a variable x1 minus x2 to get y. So denote that. So say capital Y is equal to x1 minus x2. So again, they are the random variables. The y, x1, x2 capitals are random variables. You have the samples denoted by small letters. That's the convention, correct? Now you see you have two possibilities, right? Like xi comma 1, I can have x1 comma 1, x2 comma 1, right? So x1 comma 1 means when s11 comes into picture, x2 comma 1 comes into picture when you have s12. Okay, substitute the same thing. Root EB plus W1 you get for the first case, 0 plus W you get for the second case. Now what I want to do, I want to take care of the mean, right? Mean of the first one is root EB, mean of the second one is 0, right? I have to club them together to get the y, right? So y is equal to x1 minus x2. So if you want to calculate the mean of this y, it has to be both of the means should be subtracting. So root of EB minus 0, so you get root of EB. Are you okay? Similarly, if that was for 1, do the same thing for 0. Right? 0 means it is S2 plus W. So S2 plus W, I have two options. I can have S21 and S2. Right? When S21 is received, it is only the S21 is 0. So 0 plus W1 is W1. When you get S22, it is root EB plus W, isn't it? So I have the two cases now. Calculate the means. First one has a mean 0 because it is only noise. Second one has a mean equal to root EB because, right, that has a root EB plus F1. Right? Now also you define y is equal to x1 minus x2. So x1, x2 means are calculated here. Similarly, the mean of the total variable is nothing but you can do add or subtract according to the equation. If you have a subtraction over here, this will also be subtracted. Okay, so you get the answer. Now you go for a variance like we calculated earlier. Variance of y is nothing but variance of the first variable plus variable of the variance of the second variable. So my y is equal to x1 minus x2, just remember, but variance is still addition only. Okay, so mean is directly calculated. You can see that mean is equal to mean of x1 minus x2 means mean of x1 minus mean of x2. Mean will be subtracted as it is, but variance is irrespective of whatever is the operator you have here, it is getting added always. Okay, so because of which you have n naught as the sigma square. So calculate the conditional PDF assuming it as a Gaussian. So this is the Gaussian equation. Substitute and you get the value. And I want to check that when the 0 is, when there is an error, when 0 was sent. 0 was sent means y should be greater than 0. So greater than 0 means 0 to infinity. Right? 0 to infinity, put the same equation there. So that equation comes like this. Okay? It's the same procedure. Once you get adjusted to that, this will repeat, right? So just substitute, make a substitution, change the limits as we did earlier, then substitute, right? And you can see that you are going to get an error function ultimately. So normally we bring it into this shape, right? 1 by root pi into a limit and e to the power minus u square du is a error function. Okay, always that way. That's what comes into picture. Depending upon this limit value, you get whatever is inside this bracket. Okay, right. Same you can do for error for 1, right? Probability of error 1. It's a pretty much similar this thing. So it just to save time, I just have skip that. Directly you get this answer. All right. P of 1 will come like this, right? Same answer, which is P of 0. So when we assume the generation happens with the equal probability, this is the probability of error equation, right? 1 by 2 into 1 by 2. So there is a 1 by 4 for the first term. Second term is also 1 by 4. So 2 times 1 by 4 gives you once again 1 by 2. So that is the total probability of error that you are going to get for the FST. Okay. So I think we covered the majority of the portions in the revision as well.